In this video, we will be learning about a quantity called momentum. Consider if somebody asks you a question, would you rather be hit with a bowling ball or a baseball? Doesn't matter how fast they're going. So bowling balls typically have a mass of around 5 kilograms. And if we think about a bowling ball traveling at 5 meters per second, is there a speed that a baseball could be traveling at to make its impact on you equivalent to that of the bowling ball, or perhaps even worse? And what would that velocity be? How would we know? To answer that question, we'll look at a quantity called momentum, which is something that is determined by how hard it is to change the motion of an object. So if you think about how hard is that ball going to hurt when it hits you, that all has to do with how hard is it to change the motion of the ball. And it turns out that how hard it is to change the motion is going to depend on the mass and the acceleration of the ball. To put this into slightly different terms, so we start with our familiar equation F equals ma. If we think about A, acceleration is really a change in velocity over a change in time. So if we rearrange this formula, we take a familiar formula F equals ma and turn it into a slightly different formula, which is a force times a change in time, and this quantity, force times change in time, is known as an impulse, is equal to a mass times a change in velocity, and this is a change in momentum. So this equation, F delta t equals m delta v, is known as the impulse momentum equation. In this equation, P, come on, got an extra E on there, I'm trying to get rid of it. And it won't let me. Well, there's no E in momentum. P is the product of mass times velocity, and it's equal to momentum. So if we think back to our bowling ball and baseball problem, if we have the same momentum from the bowling ball and the baseball, then it'll have the same amount of impact. Of course, the baseball at that point probably would hurt worse because it has a smaller area, so it'll exert more pressure on you when you're trying to stop it. But that gets into some other things. Okay, so if we look at an example problem, how do we use this impulse momentum equation? If we look at a baseball again, which is pitched horizontally at 38 meters per second, and then after it's hit by a bat, it moves off with a velocity of negative 38 meters per second. The first question is, what is the impulse of the bat on the ball? Well, the impulse is going to equal to the change in momentum. So if we know what the change in momentum is by looking at its change in velocity going from 38 to negative 38 meters per second, so the change in momentum is equal to the mass times change in velocity. That equals 0.144 kilograms times negative 38 meters per second minus 38 meters per second. Remember, when we look at change in something, it's always final minus initial. So that will equal negative 11 Newton seconds. Newton seconds is the most convenient unit of momentum. A Newton is a kilogram meter per second squared, and so a Newton second works out to be a kilogram meter per second. So if you look at, you multiply these two units, kilograms and meters per second. But Newton seconds is just the easiest to write down. If we look at what force caused the impulse of the bat, if the bat and the ball were in contact for 0.8 milliseconds, so then we can look at the equation force times change in time is equal to the change in momentum. Or we can rearrange to say that force is the change in momentum divided by the change in time. And we get that negative 11 Newton seconds divided by 8 times 10 to the negative 4 seconds, that's what 0.8 milliseconds would be negative 14,000 newtons. Notice that the direction of the force and the direction of the impulse are the same direction. And the reason why it's negative is because the ball was going from a positive velocity to a negative velocity. If we look back to the consequences of this impulse momentum equation, we can see that you can change the momentum by a great amount, either by having a high change in velocity, would be a high change in momentum, and require a large force. But we can change the amount of force needed to change the momentum by changing the time. So if you have a small amount of time like that impact between the bat and the ball, you're going to need a great force. If instead we try to get that ball moving over a much longer period of time, we're going to need a much smaller force. Well, if we remember back to Newton's third law, we know that for every force on an object, an equal and opposite force is exerted by that object. So because the ball exerts an equal and opposite force on the bat, as the bat exerts on the bat receives an impulse from the ball since the ball is receiving an impulse from the bat. Since the bat put an impulse on the ball of negative 11 Newton seconds, the impulse of the ball on the bat just has the opposite sign, but the same net magnitude of 11 Newton seconds. We need to understand that momentum is a conserved quantity, which means as long as there are no outside forces on a system, the momentum of a system is conserved. Sometimes you'll see in cartoons where somebody wants their sailboat to move, and so they blow on the sail, and the sailboat moves forward. And a lot of times we know right away, well, this is ridiculous. I mean, nobody could ever blow hard enough to make a sailboat move. The thing, because of conservation of momentum, it doesn't matter how hard you could blow, you would never get that sailboat moving forward. Because if all the force of if the sail caught all of the wind, then there would be a forward force on the boat. But the thing is, because you are on the boat and you are blowing it, there would have to be a backwards force or a backwards impulse on you. So the impulse of the wind on the sail to move it forward would completely counteract the impulse on you moving backwards, and so the boat would not move. The best bet would be if some of your air is spilling off the sail and not making it into the sail, that you would push backwards. So this boy on this fictitious boat would be better off turning around the other way and blowing out the backside. That would work out much better. The conservation of momentum can be put mathematically, of course, which is the sum of all the momentum you start with, which is what this sigma pi means. So sigma means sum of, is equal to the sum of all the momentum finally. Without the sigma, we could restate this as the momentum of A plus the momentum of B plus etc., equals the final momentum, which is what this tick mark means, of A plus the final momentum of B plus etc., etc. And finally, if we substitute that momentum equals mass times velocity, we can put it MAVA plus MBVB plus etc. equals MAV prime plus MBV prime plus etc. So this final version down here of the conservation momentum is the way we most often use it, the way it's going to be the most useful to you. If we look at an example problem with this, a father who is 80 kilograms and a daughter who are 40 kilograms are at rest on the ice skates. If the father pushes off on the daughter and she moves off at 2 meters per second, what is the father's speed? So if we look at this in terms of conservation of momentum, we look at the momentum that the father and the daughter have together before he pushes on her, and the momentum they have after have to be the same. Well, if they're at rest before, their momentum is 0. Afterwards, even though both of them are moving, their combined momentum must still be 0. So mathematically, we can see that, again, their momentum before 80 kilograms times 0 plus 40 kilograms times 0 meters per second is 0 Newton seconds. Afterwards, the father has a momentum of 80 kilograms plus V, 80 kilograms times V. The daughter has a momentum of 40 kilograms times 2. So 0 equals 80 kilograms times V plus 80 Newton seconds. If you solve, V must be not 1. I forgot. I don't know why this isn't letting me select to put any text in here. But it shouldn't be 1. Well, there we go, finally. But it should be negative 1 meters per second. I had a little bit of a sign error there. Sorry about that. So this is just one example problem. We'll be working many example problems, or we'll work a few example problems in class, and then you'll do more in homework and more in labs to practice this. But this should be enough to give you a good start for how to do momentum.